Hello, I am Masa and I'm presenting on camera self-calibration using human faces. Camera calibration is the problem of solving the intrinsic camera parameters of a pinhole camera model. Given a camera, 3D points for a known 3D object, for example a planar checkerboard, and its observation as 2D points. The intrinsic camera parameters can be solved as a projection of the 3D points onto the image. Typically, this process is a manual process done offline. The work is laborious and must be done for every camera, as the calibration parameters can often change once a camera is shaken or zoomed. In order to make the task easier, we propose to use a common object found in many videos and images: human faces. By utilizing the vast accomplishments of facial landmark detection and 3D morphable models, we acquire 2D landmark points on each frame of a video and fit the landmarks of a 3D morphable model to the 2D points, while simultaneously solving for the intrinsic camera parameters. Our method provides a new way to perform camera calibration by using a human face as the calibration object. This allows for calibration of videos where direct access to the camera is not readily available, and a variety of scenes assuming a human face is present in the video. With our method, we are also able to predict real-world metric depth to each person's face by utilizing the 3D shape and predicted calibration information. We test on a variety of different scenes and can accurately predict depth and calibration parameters. We find that the more frames provided for predicting the calibration information, the more accurate our results become. Camera calibration is of utmost importance in order to upgrade any 2D information into 3D metric units. For example, a possible application is to combine it with modern monocular depth estimation and predict the length of several household objects as seen here. Camera calibration information is a missing link between 2D images and more useful 3D metric units. However, accurate camera calibration without a calibration object is often challenging due to noise in 3D and 2D point estimations. We find that a significant problem with current self-calibration methods is the sensitivity of the calibration parameters and 3D predictions to noise. We show that our method consistently works best compared to all previous methods when noise is applied to the 2D observations. Additionally, when 3D shape of the face is concerned, our method will consistently have better 3D shape estimation thanks to the usage of a parametric face model. Our method can be split into two parts: training on synthetic data and optimization of output camera parameters and 3D points. To utilize human faces as a calibration object, we first generate a synthetic training set using 3D landmark points acquired from a parametric 3D face model. This synthetic 3D data is used to generate 2D sequences with varying pose and camera parameters in a smooth sequence. We add noise to the generated synthetic data to make the models more robust. Two separate networks are then trained to predict focal length and the parameters of a 3D morphable model, given a sequence of 2D points as input. For optimization during testing, we take real videos where a human face is present. We annotate each frame in the video with facial landmark detection. Then, reusing our pre-trained models for G and H, we make an initial prediction on the 3D shape and camera calibration parameters. After making the initial prediction, the networks are then removed to optimize the initial predictions further. Now, given the 2D points, the 3D points, and the camera parameters, we compute the pose using a standard PMP algorithm. This pose, 3D points, and the camera can then be used to predict a new set of 2D points, corresponding to the original input. Finally, we perform an alternating optimization of the 3D shape first, then the camera parameters, in an alternating fashion. This is all possible without any information about the true camera or 3D face. To verify the effectiveness of our method, we test on both synthetic and real data. Here we show the simultaneous optimization of camera calibration parameters and 3D shape on sample synthetic data. We compare with state-of-the-art camera self-calibration algorithms, which can handle the variety of scenes in several different evaluation datasets. Differing methods can only predict certain camera parameters, and not all methods can be used to predict 3D shape. For focal length and depth estimation, our method is consistently the best method in this generic task. To show how the number of frames and 2D landmarks can affect the error, we perform additional ablation on the number of frames and 2D landmarks. Our results indicate the importance of using video data and larger numbers of 2D landmarks in order to perform camera calibration. In conclusion, we propose a method which performs camera calibration by utilizing a 3D and human faces as the calibration object. We demonstrate that our method can work for a variety of both synthetic and real data and is the best for solving camera calibration parameters and depth to the face on the camera self-calibration problem. Thank you for coming and listening to the presentation.